Okay, morning everyone. I'll just start with a kind of brief introductory talk. Just want to maybe a few people still just coming in, but let's just get this. Okay, hopefully you can all see the. So I'm just going to give a very brief overview of ARCHER2 training. Let's take 10 minutes or so, then we'll get on to the actual technical content. I'll just have to rearrange my windows here. There we go, fine. So this course is given as part of the ARCHER2 service. I think it's important to realize, though, it is a general course, and we're hopefully explaining how parallel I/O works. But we'll be using ARCHER2 as a specific example. But almost everything you learn should be applicable to any system you use. ARCHER2 is the UK National Supercomputer Service, managed by the Research Councils and EPSRC, and we, EPCC, are housed, operating, and supporting the machine. It's actually an HPE machine. Under that service, we also provide training through the Computational Science and Engineering team, which I'm part of, and we do about 60 days per year at various locations, quite a few of them online nowadays, and all the courses are free to all academics. The ARCHER2 system itself is located at EPC's ACF Advanced Computing Facility, which is about 10 kilometers south of Edinburgh. This is just sort of an artist's rendition of this system. This is a nice picture. So that's what the machine looks like now, with all these funky cabinets. But you can't really. This was an early installation of a test and development system of just 4 cabinets, and that's quite nice because you can see the back of it. You can see all the wiring and the engineering that goes on in building a big system. This is another machine, Cirrus. Actually, we're not using that for this course. We have in the past used Cirrus. And I said we're EPCC. What is EPCC? Well, we've been around since 1990. Originally, it's the Edinburgh Parallel Computing Centre, but now we're just EPCC. And we've been running national supercomputer facilities for over 30 years. And we were recently named the first UK National Supercomputer Centre, which was nice. There's well over 100 staff now doing a range of academic research and commercial projects. And we also do postgraduate teaching and obviously HPC training. The reason I mention this is, if you go away from this course and you think, well, that was very interesting, but I'd like to collaborate with EPCC in the future, a lot of our staff, a lot of us are involved in collaborative research. So we're named on research grants with collaborators. And in that sense, we're just standard University of Edinburgh employees, research assistants. So we often get involved in research grants with other groups around the UK and beyond. So this is a picture of Edinburgh, which does look a bit like this today. I know it's an online course, so I thought we'd show a picture of Edinburgh. Given you're not going to be here, unfortunately. There are some key ARCHER2 resources, but actually, so this isn't really a course about ARCHER2. Hopefully all the exercises, everything should be pre-packaged and just run out the box, but that's just there for reference in the future. Who am I? Well, my name is David Henty. I'm in charge of education and training at EPCC. That encompasses the on-campus MSc programs, which I'll mention very briefly, courses on the ARCHER2 training program, and some commercial training. And in terms of HPC research, I'm interested in generally new parallel programming models, general performance, parallel I/O, just a range of performance-related issues with HPC parallel computing systems. Please fill the feedback form. You'll be sent a link at the end of the course. If you have any general inquiries afterwards, you can contact the support desk, the help desk. The feedback, we do take it seriously. We like good feedback because we can tell EPSRC how good we are, but also critical feedback is also important because it allows us to help our training in the future. And we do review all the feedback. All the feedback is reviewed and at one of our weekly meetings. So we do run an MSc in HPC and HPC with data science. I mean, probably not of interest to you, but it might be interest to people that you work with or that you know, or undergraduate students you're aware of. So it's a standard UK MSc over a full calendar year, about 8 months teaching and then 3 months of research dissertation. This is graduates from actually quite a long time ago. We also we developed a MOOC, a massively open online course under the PRACE project, which was a European project we were in, and although that I mentioned it here because again it's something you're probably not interested in yourself, but it might be interesting in your colleagues. We now run this under the ARCHER2 banner, so they need to slightly update this slide. Yeah, so actually this is sorry, this is slightly out of date. It's actually available as a self-service course, accessible from the ARCHER2 training page, and I'll point that out later actually. During the course, which is just a one-day course, you'll get access to the machine. We're using this TA216 project today, and that will allow you to access for about up to a month afterwards. The accounts will be closed 2 weeks after the access ends, and files, etc., will be deleted. I don't think that's particularly, you're not really doing any development here, so there won't be any files to take off, but just be aware of that. You do have access for a month after the course, just if you want to do additional stuff. And carry on with the exercises, but don't worry about the materials, the slides, the exercise, etc. will be available on the ARCHER2 website for a long time. And this session is also being recorded, so after the session, all the slides, all the material will be there. It will just be a snapshot of the course as delivered. Plus, there'll be recordings of these lectures as well. Longer term, and you might go away and say, well, that was all very interesting, but how do I get access to ARCHER2? You can apply in a standard way, like you do apply to access to any national service through the research councils, but all of these require some kind of justification. Obviously, you have to explain why you want to use the machine. There is something called the pump priming access, which is the lowest barrier to entry. But of course, you get this catch-22 that you might want to apply for long-term research access to ARCHER2. To do so, you have to prove you can use ARCHER2, but you can't prove you can use ARCHER2 till you can access it. And to break that loop, we have something called the ARCHER2 driving test. So if you go and do this driving test, and it's basically checking that you have a basic understanding of parallel computing and have read some of the ARCHER2 documentation. If you get access under that, you get 800 compute units for up to 12 months. A compute unit is a node hour, and a node on ARCHER2 has 128 processors. So this is, although this is a relatively small amount of time on the ARCHER2 side of things, this is like running on your laptop for 3 or 4 years or something like that. So, but it is a way of getting access to ARCHER2. This isn't valid because this is not a face-to-face course. There is a code of conduct here, just to say, we do expect everyone to be constructive and help each other. We all come from very different backgrounds. What may be obvious to you may not be obvious to somebody else, and vice versa. So if there is, if you do have any concerns about anything, then there is a web form you can access to report any issues. This isn't, of course, about ARCHER2, but I mean, just very briefly, ARCHER2 has about 6,000 nodes, each with 128 core CPU. That's about 750,000 CPU cores. Like any big system, you don't access it directly. You use it via Slurm, the Slurm batch system, and hopefully, again, that should be prepackaged. This is all explained on the sheet, but it is important to notice you have at least two file systems on ARCHER2. And you will, when you log in, you'll end up in your home file space, home TA216, TA216/ whatever your username is. We need to run in /work because the home system isn't visible. A, the home system isn't a parallel file system, and B, it's not visible from the compute nodes. But again, I have hopefully prepackaged that all and scripted it in the exercise sheet. And we have reserved queues. So for today, from 10 till 4, we have a reserved queue, so you will get fast turnaround for your jobs. So hopefully you won't have to wait for anything to run. So I hope you enjoy the course. Please ask questions. As I said, the material will be there for forever, whatever forever means on the web. But I mean, hopefully being online just now allows you to ask questions. I'd rather spend time answering the questions you're interested about than going through slides, which you can look at afterwards. Please, if you have any questions, ask. There is a chat in the bottom. There's a little bubble icon, and you should. I just hope someone type into the chat. If you want to, for general, I get a notification if there's a chat message arrives. So if you have a question, rather than using the audio, which can cause something. I mean, obviously, if longer discussions will kick up the audio, but there is a chat session there, and can someone see it? You maybe have to open it up. There's a little chat bubble. Yes. Okay. Well, thanks. So yeah. So that's good. So I get a little audio notification of that, and so it would be good. That's the best way to answer something during the slides. I'll turn my volume up a little bit. That's good. Okay. So that's really it. I will now give the first. Oops. I'll give the first technical lecture. Let's get this set up. Okay, Eva. Okay, thanks. So I was gonna, yeah. So Eva, you had some problems with the getting on. That's good that you got on. So that's good to know that you've. So what I will do now is, sorry, I've got a bit too many windows to manage here. So what I will do actually, just to start with, actually, I will just point you to where the materials are. So hopefully you've seen this, but it's taking a while. Oh, there we are. There's a bit of a delay. It's taking a few seconds. Anyway, so this is the ARCHER2 main page, and from there you can access the training page. And there's upcoming training, and that is where we are at the moment, Efficient Parallel I/O. The MOOC I mentioned, the Massively Open Online course, is now available. So these courses at the top are self-service. They're always open. We have MPI, and we also have the hands-on Intuitive HPC, but we have Efficient Parallel I/O. And actually, just to show you later on, this will move to the past course materials page where we have a repository of everything we've ever given. Quite a lot of stuff there. Let's look at the upcoming training, Efficient Parallel I/O, and this is the main page with the timetable. But you'll also see that there is a course material. So what will happen is the videos will appear here, but this course materials page is to link to a GitHub page where the repos a bit, I would follow, hopefully you can follow it. So this is today's course, and there's quite a lot of stuff lying around in the repo. So I would recommend that you access stuff from these links. So these links link to all the relevant stuff. And I've not updated the date there. That's a bit poor. I've updated it here, but I haven't updated it here, so I will fix that. But actually, this is a bit page for today. These are the courses. This links to the actual slides, the PDFs, a couple of reports here, but also there's an exercise material here, and that's the main website. That's the Git repo we're going to use for the exercises. But hopefully everything should be there on this page that's relevant for today. And if I just basically take 2 seconds, and I will, yeah, 2 seconds, we're fixed now. Okay, so that's where all the material is, but I'm now going on to give the actual first talk. So what I'm going to cover here is what the challenges of parallel I/O are. Yeah, there's the slide. So really to try and set the scene, I mean, parallel I/O is a huge topic, as is I/O itself, but I hope that going away from, and people have a lot of different challenges depending on what their application is, what their use case is, what their data, what their workflows are. But I hope you need to have a simple conceptual model of what's going on, and it's not magic. It's very complicated in detail, but conceptually it's really quite straightforward, and you need to have that conceptual understanding. So hopefully that's this talk, is to try and discuss what the issues are from a conceptual level, and then we can use that to try and understand some of the performance results we're going to get later on. So first of all, I'll cover why I/O is difficult in just I/O itself, why parallel I/O is even more difficult, and some of the straightforward solutions that people use in parallel, and then a bit about what we're trying to achieve. And these last 2 things, this course used to be much more focused on actually programming and using MPI I/O. I've moved away from that because it was becoming a bit not particularly relevant. So, but I'll mention that very briefly. And the main thing here is to try and understand, have a conceptual model of what's going on. So why is I/O hard? Well, it breaks out this nice process memory model. And when you write a program, you run it, you have this process which has access to memory, everything's nice, it just runs and does its stuff. But when you write data, it has to physically appear on an external device. It has to appear on a physical disk somewhere. And that's nasty. Files are very restrictive compared to data. Data arrays are random access. You can go anywhere all over them. Files aren't. Well, you can randomly access a file, but it's very inefficient. To move, at least on a spinning disk, to move to a different point in a file, you have to physically move the head of the disk, and that's very slow. And so, Philo is designed for linear access, start right to the end, but that might not be the way that your data is arranged in memory. You may need to remap your program data to basically have it, formatted so you can easily write it to file. It's very system specific. There's lots of different setups on different systems. For example, you could have text, binary. If you're writing floating point numbers, they could be big or little endian, depending on where your system comes from. Fortran has this unformatted, weird, undocumented format. You can be using libraries like HDF5 or NetCDF. It's very, very complicated, lots of options. The disk systems themselves are very complicated. An individual disk itself, maybe multiple disks. RAID stands for redundant array of inexpensive disks, I think. There's many, many layers of caching, and when you write to disk, because disk access we'll see is very slow, it probably doesn't write to disk, it probably writes to memory. I think I/O is the HP equivalent of printing. You buy a new laptop, you plug it in, you connect to the internet, everything works fine, no problem at all. But then you try and actually print something to a printer, and it's a complete nightmare. So this is a very simple example. Imagine I have written a program, and this is a C program. I have a double array, double X44. So I have an array of 16 doubles, i.e. 128 bytes. Okay. If I want to write that to memory, I can F write X, size of double, 4x4, 16 to and I assume I've opened a file pointer beforehand. Okay, so it doesn't really matter how I draw things, but this array of 4x4 doubles is made up of 16 actual doubles, and I've laid them out as if they're written. So I've drawn them so that they're laid out in this order: 1, 2, 3, 4, 5. You can argue about should these be row major or column major. It doesn't matter. This is the order I'm going to use. And so basically, when you write this data out, you have a 4x4 array of 16 doubles, and when you write it out on file, it just becomes a linear block of 16 doubles, numbered 1 to 16. Okay. So you've lost that memory of it being a 2x2 array. A 2-dimensional array. I've also overlaid a color here, and that isn't relevant in the serial program, but it will become relevant in the parallel program. In the parallel program, we're going to split this up amongst processes. And you can see that the crucial observation here is that even in this completely trivial example of a 4x4 array of doubles written straight out to disk, if I split this array over processes, this processor here, although it owns a little 2x2 subsection, that is not a consecutive contiguous subsection of the output array. So you have this, the biggest problem in HPC in parallel I/O is you have to map not only the individual data to a file, you have to somehow or other make sure that the data which is contiguous, which is a solid block on a particular process, is then scattered to the correct place in the file. So if we want to do parallel I/O, we've seen here that the data will not be a single contiguous, although we imagine it as being a big 4x4 array. We'll have split it up amongst 4 processes, process 1, 2, 3, and 4. And each of those has a little 2x2 array. So each of those only has a little contiguous array of size 4. The problem is it's really quite complicated to actually get that data into the right place in the file, because clearly we want to reproduce the same file we had in the serial program. Well, that's my opinion. And so there is insert magic parallel I/O call here to do that. And there's quite a lot to do here, okay? These processes have to access the same file. They have to access different parts of the file. Their local data has to be split up into although this data here is contiguous on process 4, it's non-contiguous in the file. So there's quite a lot going on here. So even before you start talking about performance, it's actually quite a complicated thing to have to do. So what do some people do? What are naive solutions? Well, in my MPI program, my parallel program, I don't have a global array of size 4x4. In this decomposition, I have a little local array of size 2x2. I could open we could all open the same file, and we could all seek to some offset and do a write. So we could basically just open this file, yeah, and the blue guy can say, well, I'll skip to here, write this data, then skip to here, write this data. The performance of that is going to be appalling for many reasons. Multiple processes writing the same file is problematic. We'll come back to that. The performance will be very poor. It will require many cycles of seek, write, seek, write, seek, write. So okay, and that is file systems, serial or parallel, are optimized for open a file, write 10 gigabytes of data, close the file, not open a file and dibble around writing tiny amounts of data all over the place. So this will, this will not work in general in principle, because as we will see in a couple of slides time, multiple processes writing to the same file is problematic, but the performance will also be terrible. So why is parallel I/O harder? Well, we can't in general have multiple processes writing to a single file. Okay, Unix generally can't cope with this. Okay, Unix, when you open a file, okay, Unix assumes that in some sense that you're the only person. It's up to you to manage that. It doesn't understand that multiple processes will be writing to the same file. Okay, if you ever accidentally opened the same file twice in different editors on your laptop, you'll see that all hell breaks loose. And the main reason is that we'll see that data is cached in units of disk blocks, and we'll say what that means, but it's not coherent. In other words, you can get the wrong answer if multiple processes write to the same file. Now, if you have a parallel file system, it may be aware of that. It might say, well, I'm going to allow multiple processes to write to the same file. But to do that, they may just lock the file. They might say, okay, I'm a parallel file system. There's multiple processes writing to the same file. I will lock the file. Well, that means this way of writing data is even worse. Not only is each process writing very slowly because it's going open, seek, write, only one process can write to the file at a time, because the file system is locking the file to prevent any conflict. And so naive solutions can be incredibly slow in parallel. And I should say this as a caveat. The difference between writing a good I/O pattern or good I/O solution and a poor one can be orders of magnitude. A bad solution could be 1,000 times slower than the good. It's not like performance optimization. I'll make my code a little bit 50% faster. If you get it wrong, your performance can just be atrocious, and that's one of the problems. Even reading can be difficult. You could say, well, okay, this is a problem with writing, but if we were reading this data, each process could just read its own section of the file. Isn't that okay? Well, if you have 1,024 or even more, tens of thousands of processes opening a file, it can completely overload the file system. Just can't cope. And as we've seen here, data is distributed across different processes. Processes do not, in general, own a contiguous chunk of the file, and you may not even want to write out all the data. If you do a standard parallelization in a regular grid decomposition, your local data may have halos, and they'll need to be scripted. That's junk data. You don't want that to be in the file. So just to illustrate what some of the issues are, just to say why in principle simultaneous access to a file from multiple processes is difficult. So we've got a file, and we've got two processes, process 1 and process 2. We want process 1 to write the first half of the file and process 2 to write the second half of the file. And you might think, surely that's fine. Surely if two processes are writing to different parts of a file, then there's no problem. But there is actually a problem. So in reality, when you write to disk, the minimum quantum you can write to the disk block. Okay? When you write to disk, the minimum you can write is actually a disk block. And that tends to be 4 kilobytes on a standard system. It might be megabytes but I/O is done in quanta of disk blocks. And so what can happen there is process 1, and that allows each process will have a disk cache. So to try and make writing to files incredibly slow, and so to improve read and write performance, all operating systems will cache as much of the data as they can locally in memory so that it is fast. So each process has its own disk cache. So process 1 wants to read the first half of the file, but it can't read. It can only do the I/O in quanta of the disk block. So actually, it reads the first 2 disk blocks. Okay, and then and also process 2 reads the second 2 disk blocks, disk 2 and 3, and then the data is actually read into the memory. So what has happened is that the processes, although they only need to know the first half of the file, they have to do I/O in units of a disk block. So it's read in, each of them is read in 2 disk blocks. Okay. So then process 1 updates the file, and process 2 updates the file, and then process 1 writes to the file. Now, of course, when you write, you basically don't write to the file, you write to the local cache. So process 1 writes to the cache, and process 2 writes to the cache. And that's all very fine, except at some point down the line, maybe when you close the file, when your program terminates, you're going to actually have to flush this data out to disk. You're actually going to have to, in the interim, you're reading and writing to a local copy, but at the end, you have to flush it to disk. But I/O is only done in units of disk blocks. So process 1 will flush that data to disk. That looks fine, but process 2 will flush that data to disk, and you get a conflict here. You get the wrong answer here, because now this could have been solved through various locking, but this is the in principle problem. To optimize file I/O to make it even go at a reasonable speed, operating systems cache data as much as possible, but they are in general not aware of the parallel nature of modern computers. I mean, when was Unix written? 50 years ago. It doesn't work, and so this is yet another problem. Now, parallel file systems can solve this, but it is still an issue they need to solve. So the other naive solution you see people do is independent I/O, or called file per process. Each process opens its own data file and writes the local data. So this is really, really easy to implement, okay? But in practice, a nightmare to cope with, because first of all, you're asking the file system to open tens, if not hundreds of thousands of tiny little files, and that is, we'll see, is not efficient. But also, once you've written your program, once you run your program, you have a directory full of tens of thousands of files. They're not of any use to anyone. So you spend up an enormous amount of time doing pre and post processing. Okay, so this is in practice often a nightmare to cope with. Also, the data format depends on the number of processes. And so you're getting completely different output from the serial code. I find this philosophically wrong. Parallel computing should get the same result, but faster, not a different result. So what I'm saying here is what I want is when I write this out to disk, apologies, difficult to go forward in my anyway, I want to get this file here, a single file of size 16 with the 16 double precision numbers in it in the correct order. What I get if I do file per process or naive individual I/O is this. So everyone opens their own local file, they write it. Now this can be quite fast up to a point, but you end up with 4 data files: data 1, data 2, data 3, data 4. Somehow down the line, you're going to have to recombine them, and that is a real issue. So this is what we want to achieve. We want the parallel data to be written into a serial file in the correct order, where the correct order is the order we got from the serial program, that the data is ordered as it would have been on a serial code, and the data is ordered independently of how many processes you run on. The naive first solution is controller I/O. Well, why don't we just send all the data to and from a single process? So basically, we basically say we nominate in an MPI program rank 0 as the boss. Rank 0 just gathers all the data and writes and reads a single file. So the advantage of this is the output is the same as the serial code, but there's 2 issues. One is we quickly write to memory on the controller. It's very unlikely you'll be able to store the entire data set on a single process, but you can then write in many small chunks. The major problem is only a single process is writing. By definition, in controller I/O, in naive file per process, every process is writing, and the problem there is that can overload the file system. In this situation, only a single process is writing. We'll see that you then get no benefit from a parallel file system. Your I/O rates will be spectacularly slow here, but it at least gives you what I would consider to be the right answer. So what we need, if we want to do parallel I/O properly, where the I/O system deals with all the system specifics, so we can go to run on another HPC system. We don't need to worry about all the details. We want a single file format, where it looks like a serial file. All files should save file in serial format. Entries are stored according to their position in the global array. I mean, you could also say, well, I could say, rather than doing a file per process, I could open a single file, and the first process could write the first quarter of the file, the second process the second quarter. Well, there you do get a single output as a single file as output, but the order of the data depends on how many processes you ran on, which is not, I would say not ideal, not acceptable. A number of libraries exist. We will consider MPIIO. Now, I would not recommend nowadays that anyone programs. So I used to run a whole course on parallel I using MPIIO, parallel IO using MPIIO. I would not recommend that anyone does that, but as their first port of call. However, almost all these IO systems, these higher IO libraries, use MPIIO under the hood. And so one of the reasons why benchmarking MPIIO and having a basic understanding of what it does is useful is that other IO libraries either use MPIIO or will use effectively the same approach. And what the important point you need to do is in any parallel IO system, the IO system needs to know how the local arrays should be stitched together to form the file. You need to tell the IO system, here I am, I've got some data, and by the way, this isn't just my data, this is a subsection of some global file, and I want you to work out how to map my local data into the global file, either for read or for write. The important point is the mapping from the local data to the global file is only in the mind of the programmer. You may think that you have 4 MPI processes arranged in a 2x2 grid, but actually that's just in your mind. That's not explicit in an MPI program. So it's implicit. And so any parallel IO system will have an important step where you open a file, and then at some point before reading or writing the data, you tell the IO system, I own this subset of the global file. And each IO system has a different way of doing that, but it is the crucial step in parallel IO. And so the programmer view is that you have a 4x4 array distributed across a 2x2 grid of processes. The computer has no idea. The computer says, I'm running 4 processes, 1, 2, 3, and 4. Each of them has an array of size 4. Okay, that mapping that there is not explicit. So you have to have this extra stage in parallel IO to say, this is how my local data maps into the global file. And the easiest way to think of that is to think of the file as a large array. That's the way it works. That basically, imagine we are recreating a single large array on a controller process. You're basically saying, imagine that there was a controller process that had this big array. I own this top right-hand corner of it. The other process owns the bottom left-hand corner of it. However, what you're hoping is that when you do parallel IO, the IO system creates this array and saves it to disk, but doesn't actually ever create the entire array. It doesn't do naive controller IO. So, for example, what you want it to do is do a small number of large IO operations and utilize any parallel features. That's all. So this is. We'll come back to that in the next lecture. We'll talk about how this works in practice. In MPIIO, just out of interest, it's part of the MPI standard. Each process needs to describe what subsection of the global array it holds, and it's up to you to check these don't overlap. And the way it's done in MPIIO is it's done using derived data types. So MPI already has a concept of if you have a local array, okay, you can tell MPI to send non-contiguous subsets of that array through derived data types. You can say, I want to send a message which is the bottom right-hand corner of this array. And how you do that in MPI is you create derived data types. They can be vectors or things called subarrays, which say, of my local array, I want the message to be this subsection of it. MPIIO hijacks that and says, well, we'll use the same mechanism, but what we'll use it is for a process to say, not what portion of a local array it owns, but of this mythical global array, okay, the entire data set, I own the bottom right-hand corner of this global array. So it's just a sort of hijacking that mechanism to do something different. But other IO systems will have different ways of doing it, but that is the critical step in parallel IO. MPI is usually the lowest level one. You may never call it directly, but higher level libraries exist. A lot of people use HDF5, NetCDF, or more modern one is ARCHER2. All of these have the same approach. At some point in between opening and then doing actual I/O of read or write, you will specify some way of describing what portions of file each process owns. And these libraries usually use MPIO to do their reads and writes at the lowest level, usually. So summary, parallel I/O is difficult in theory and in practice. MPIO provides this high level of abstraction where the user describes the global data layout using these derived data types. And MPIO hides all the system-specific file system details, but hopefully takes advantage of them. We'll talk about that later. There are more flexible formats, NetCDF, HDF, and ARCHER2 are the ones which I cover and that my benchmark can utilize. They gain, as I said, performance by layering on top of MPIO, but MPIO requires, to do MPIO itself requires a good understanding of derived data types, and we won't go into that level of detail in this course. So that's the end of the first. Are there any questions about that? I haven't seen any coming in. So I'll take a 5-minute break for the next lecture, but there'll be a chance later on to ask any questions you might have specifically. So let's so let's restart at 10:15, and basically I'll give another lecture, and then we'll just before the coffee break, we will just check everyone can get logged on and run the example. But I'll be back in are you going to cover I/O in multiple GPUs? Oh, that's well there's no, so yes and no. Okay, so basically my assumption is that the way you do parallel I/O on a GPU node is you copy the data back to the CPUs and then do I/O. So there is that is the night. There may be ways of GPUs writing direct to memory, but the standard way you would do it, at least in an MPI program, is you would just bring the data back onto the CPU, CUDA mem copy or whatever you do, and then write from the CPU. So GPUs are really dumb. They can't run programs themselves. Every GPU has a host CPU, which is where your MPI process runs. And so parallel I/O from a large GPU system is just the same as parallel I/O from a large CPU system, assuming you can get the data from the GPU onto the CPU, which would be your first port of call. Does that answer the question? It's a good question, but I mean, GPUs, to a parallel computer, GPUs are just, it doesn't even see them really. But I don't think there's any difference. I don't believe, now correct me if I'm wrong, I'm not a GPU expert. Well, actually, no, because actually on a GPU system, you've got the exact advantage that on a CPU system, the process, your CPUs are either doing I/O or doing computation. And so while you're doing I/O, you're not doing computation. But on a GPU system, the GPU and the CPU can operate asynchronously, and so you could have the CPUs doing I/O at the same time as the GPUs were doing calculation. So that would be, yes, in the naive, I/O can always come to dominate the time, and that's why we need to make it faster. However, on a GPU system, you do actually have the ability to carry on doing computation while you're doing I/O. Yes, yeah, exactly. But that's just because GPU systems are really rather badly built. I mean, GPU systems take an incredibly quick GPU and attach them to an incredibly quick CPU with a soggy bit of string. That is being fixed, okay? But for the past 5 or 10 years, that has been the problem. Yeah, but that's the problem with GPU systems, not to do with I/O. That's just saying that GPU systems, until recently, weren't really that well built, but that has been solved. Presumably, when you say someone there's $1 trillion market out for fast GPUs, they go away and solve the problem. But originally, GPU systems were just a CPU. Somebody stuck a GPU on it across a PCI interface, a soggy bit of string, and it's just been very difficult to use for real calculations. But the current and next generations are solving that they're built, yeah. But you're right, it is a problem copying data, but that is not an IO. That's not an IO issue. That's an unfortunate feature of current GPU architectures. Okay. So Oakley asked a question: will you cover how luster striping and data blocks? What do you mean by data blocks? That's just I think so it's a good question. I will cover luster striping. I don't quite know what you mean by data blocks. You're talking about how I talk about this. They don't. So that's a good question, but the you don't really care in some sense. A luster stripe is conceptually the same as a disk block. It's your. I don't think there's a. I only talked about that disk block stuff to illustrate how, in principle, there's this problem with just to try and say why isn't it okay? Why isn't it trivial? Sorry, for multiple processes to write the same file, but luster takes a different. In luster, you don't really care about the disk blocks. You just care about the striping. We'll talk about striping quite a lot, but the disk block is at a low level below that. You don't have to care about it. I will talk about how luster avoids the contention that luster solves this. Well, parallel IO systems on luster solve this conflict issue in a different way. So hopefully I will answer the rest. But if I don't, come back at the end and later on ask me a question. But hopefully I will cover that. Okay, so I will now. Where are we? Can we? Yeah, fine. So what we're going to talk about now is conceptually what are parallel file systems and how does luster work. And hopefully after this this talk, you will have a conceptual view of how parallel IO works or how parallel file systems work. So I'll just make sure I've got the chat window open. Fine. Okay. So I'll cover parallel file systems, how luster works and what striping is, and some simple luster commands, and then I'll talk about where the bottlenecks are, this sort of. And we'll start to investigate that by running a simple benchmark program. So I first started to teach parallel IO about 20 years ago when I wrote a parallel IO using MPIO course, or took it over from a colleague. And at that point, I had absolutely no concept of what a parallel file system was, even what it meant. Okay? But it's actually very simple, okay? Like most things in computing. So a parallel computer is constructed of many standard processors, each not particularly fast. Okay? That's what a parallel computer is. And the performance comes from using many processors at once. So people are often surprised if you run a simple serial program in C or Fortran or C++ or even Python, it will probably run faster on your laptop than on a single processor of ARCHER2, because ARCHER2 was built 5 or 6 years ago. And it requires, but to take advantage of parallel computing, it requires manual distribution of data and calculation across processors. It's up to you to say, where is my data? How do they communicate with each other? And you can do that using MPI, for example. Parallel file systems are just the same. They're constructed from many standard disks, each not particularly fast, but the performance comes from reading or writing to many disks at once. So the file system on ARCHER2 isn't fast because it's got magic expensive disks. It's got good quality disks, but hopefully lots of them. And what the file system sees is it actually sees a cluster, and it requires many clients to read or write to different disks. So what I'm saying here is that to the file system, each HPC node appears as a separate IO client. So to the file system, ARCHER2 is 5,812 or however many individual computers called node 1, node 2, node 2 up, all writing to the same file system. So the file system sees of order 6,000 clients, but the file system itself has lots of disks. And the way that you can get performance on a parallel file system is that the data from a single file can be striped across many disks. So the way you get parallel performance in your computation is you take your data array, your data, and you distribute the data across many processes, many nodes. The way you get fast parallel I/O is a single file is actually stored on multiple disks, and that is called striping. It's striped, and we'll talk about that, how that works later. However, when you're on ARCHER2 and you do ls minus l, you don't see, if you write a file, you don't see 50 or 60 files split up. You don't see that file split up into 50 or 60 little chunks, although actually it is. You see the abstraction is it looks just like your laptop, a single file system, and that's because there's a single database which contains information for all the file. When you open a file, there's this database which says, okay, David's opened this file, but actually it's a big file that's stored on these 6 disks and that bit there, and that's called the MDS, the metadata server. So the MDS is, because you have multiple disks, you need to have a record of what's going on, because it's quite complicated under the hood, and that is a database. It's called the metadata server, the MDS. So that's okay. So striping and MDS are two of the key concepts. So the parallel file system on lots of parallel file system, like on ARCHER2, you have your application processes running on the compute nodes. Then there's a high-speed network, which on ARCHER2 is the slingshot network, and that allows these things to talk to each other. But at the bottom level of the file system, you have OSTs, object storage targets. I will call these disks. Now they're probably not disks; they're probably multiple disks together. But I will naively call these a disk. Okay, so you have lots of RAID devices. Each of these probably has about 10 individual disks. But I will call an OST, an object storage target, a disk. Okay. They're actually grouped together into servers, object storage servers, but that is hidden from you. So in terms of parallel I/O, what you care about is how many disks am I writing to, and Lustre calls them object storage targets, OSTs. There's also a physical location for the metadata server, but actually, I think that you'd better to think about the metadata server as being Lustre has metadata servers, metadata targets, object storage servers, object storage targets. I think the most logical thing is to think about there being a single metadata server. Don't really care how it's implemented. There's one of them, but this is what you interact with as a user. This is what you see. You don't actually see this level. It's hidden from you. So this is what you see. Lots and lots of disks, lots and lots of OSTs. They're called object storage targets. And so this is actually a picture of I don't have a good picture of the ARCHER2 disks, but this is the way that this was a big bunch of disks in a cabinet. It was split up into each of these is a single RAID device, but they're grouped together. So a single object storage server would have a couple of disks in it. But as I said, you don't see that level as a user. So as a user, you see multiple OSTs, object storage targets. I don't have a good picture of the ARCHER2 ones. So terminology, there's a lot of different levels of virtualization and such like, but a single object storage server has multiple object storage targets. A single OST has many physical disks in a large array. But I will talk about the MDS, the metadata server, the database that contains information, e.g. where a file is stored, and the object storage targets, the physical devices that store your data. And I will call this a disk. Okay, that is my conceptual model. So the MDS and the OST are what a user interacts with. You ask, am I overloading the MDS? Can the MDS cope? Am I overloading the OSTs? Can the OSTs cope? So those are the things I'll talk about. So metadata server and OST are what you're talking about. The MDS is the database that stores where everything is, and the OST is where the data is actually stored. So on ARCHER2, there are 3, I think there might be 4 now actually. This is something which confused me. There are actually 4 now, so this is out of date. There are 4. I should update this. There are 4 work file systems: work 1, work 2, and work 3. Each has 12 OSTs and 1 MDS. So you can imagine that this MDS is going to become potentially a bottleneck. So we have actually on ARCHER2 there's four file systems. There's four file systems. We have 48 OSTs, 48 disk storage units. If we gave everybody access to all of them, that would be good because you could do very fast I/O. You could split a single file across 48 disks, giving you very high aggregate I/O. However, all users would be accessing the same MDS, and the MDS could get overloaded. So what you do is there's this trade-off between having lots of disks on an MDS and lots of users versus overloading the MDS. And the compromise on ARCHER2 is that we actually have four OSTs, four different /work file systems, each with 12 OSTs and one MDS. And you're assigned to a different partition to share the load. Okay. So basically, when you log in, you see /work, but that's mapped to work1, work2, work3, and also now work4. The multiple file system means the MDS is less likely to be overloaded. There's also a file system with solid state disks. They're not spinning disks. They're actually like a USB, a memory storage device. We've given you access to this for this course. We expect better latency, e.g. for small I/O transactions. May also yield better bandwidth. It may also be faster and more reproducible because there's fewer people using it. So, but that's separate. But so we have spinning disk, which is the work file system, and we have these solid state SSDs, which are now configured /scratch, and each has around 3.3 petabytes of storage. That's these ones here, and so that is for. Okay, so yeah, so I've updated one and not the other. So that is why. So I apologize. This is slightly. There are four. Okay. So there's four work file systems. Each has around 3.3 petabytes of storage, and that gives us 13.2 petabytes. I couldn't correlate this with the ARCHER2 documentation, so I'm apologies, I'm not working up yet. Apologies for this, because the ARCHER. So there's this discrepancy with powers of 10 kilobytes and kilobytes, and it doesn't only much of a difference, but way up in the petabytes it does. So 13.2 petabytes, where this is done in 2 to the n, is 14.5 petabytes, where this is done in power of 10. It's quite a big 10% difference at this level. But there you go. So by default, each file is stored on a single OST. So when you create a file, by default on ARCHER2, it will pick an OST and put it on there based on the load. It will say, right, David's got access to 12 OSTs. Which one is least busy, least full, whatever, and it sticks it there. So these are automatically distributed across the available OSTs to balance the load. And each OST is actually a separate Linux file system. Each OST is actually a separate Linux file system. But you see a single one because the MDS stitches them together for you. This is called an unstriped file. Okay. So the default, so striping is splitting a file across multiple OSTs, across multiple disks. By default on ARCHER2, the default is to unstriped. That's because 99% of the files on a file system aren't big multi-gigabyte, multi-petabyte data files. They're source code. They're little, so there's no point taking a 4 kilobyte text file and splitting up across disks. That's pointless. So that's why this is the default. And actually, reading and writing multiple files from multiple nodes can benefit from multiple OSTs. So that means that this file per process approach, so we're not talking about parallel I/O, well, at least from a software level at the moment. If you have an MPI program and each rank opens its own file, then those files will by default automatically be spread across the OSTs. And so you can get very good bandwidth from this file per process model. Unfortunately, it has two issues, as we've said before. One is it can overload the metadata server because you're potentially opening and closing tens of thousands of files. But also at the end of the day, you end up with tens of thousands of files to deal with. So from a programmer level, it's a bit of a nightmare. But the important point is access to a single file will not benefit from the parallel nature of the file system, in this case, in the default case. So that's why controller I/O, where you funnel all the I/O through a single process, say rank 0, does not benefit from the parallel file system, because that file has to live, by default, will live on a single disk. Lustre gets its performance, so you can get better performance, and also this helps with lots of users. Okay, if lots of users are all writing files at the same time, they will be distributed across multiple disks, multiple OSTs. So this way of picking different OSTs for different files is a nice way of aggregating the load, but it doesn't, in principle, benefit you for I/O to a single file. How do we make I/O to a single file go faster? Well, we can't do it if a single file is stored on a single disk. So what Lustre does, it stripes the data. The parallel performance in Lustre comes from striping single files over multiple OSTs. So you see a single file, but the operating system / the file system divides the file into stripes if requested by the user. The default is not to do this. And then these are split. Stripes are read, written to from their assigned OST. So it's only worth doing this for big files, but they now are written to lots and lots of different disks. They live on different disks. So striping allows multiple I/O processes to access the same file. It increases the bandwidth as you're accessing multiple OSTs. Now, like all things, this is optimized for bandwidth, not for latency. Reading and writing small amounts of data is very, very inefficient. Okay, so you want to be able to open a file, write 20 gigabytes of data, and close it. So this is called striping, and the striping of a file is fixed when you create it. And there are two fundamental parameters, which are the number of stripes and the stripe size. So if you create a file with a stripe count of 4, okay, what it doesn't do is it doesn't assign the first quarter of the file to the first disk and the second quarter to the second disk. What it does is it tries to do a bit more load balance thing. So what it does is it splits the files up into blocks of the stripe size. So typically the stripe size is a megabyte. So the first megabyte is stored on OST1, the second on OST2, the third on OST3, the fourth on OST4, and then back to the start again. So what Lustre does with striping is it takes your file, which is hopefully many gigabytes, splits it up into megabyte chunks, and deals those megabyte chunks out like a pack of cards. So it's a round robin with a default stripe size of 1 megabyte. We can play around with the stripe size and the stripe count, but actually the default stripe size seems to work quite well. So on Lustre, you can set the striping on a directory or file. The default is not to stripe or one stripe. It's called LFS, Lustre file system set stripe, and then the count. And you can do it on a directory or a file. I find it most easy to do it on a directory. Have a directory where you do your parallel I/O, set the striping accordingly. All files subsequently created in that directory will have the striping that will inherit the striping from the parent directory. So nstripe can be 1. If you want to do if you want to stripe across all the OSCs, you don't need to remember how many there are. You do nstripe is -1, and that's full striping. You can also set the stripe size with -s, so I can set it to be 4 megabytes. That doesn't alter existing files. Okay, to change the striping of any existing file, you have to copy it. But before you create a file, you can set the striping, and that's the stripe count, how many disks it's stored on, and the stripe size. And you can inquire. LFS get stripe is a useful way of inquiring if you get lost as to what you've done. So parallel I/O to a stripe file is very complicated in practice. You have to find out where in the file does the local data live, and then where are the OSTs on the different stripes located, and then are there write conflicts coming from different processes. So we need to use a parallel I/O library to do this. But a parallel I/O library sorts out, hopefully, all these things for us. So I want to talk, there are we need to think about where the bottlenecks are, and you will hit different bottlenecks in different situations. So I've got an analogy here, which I think is relatively useful, but you may not, but I won't. So in my analogy, okay, we have lots of people trying to get out of a train. So a train is drawn into a train station, and you all want to get out the train station. So getting out the train station means leaving the train station through different doors, okay, leaving the platform, apologies, through different doors. So the disks, the OSTs, are like the exit doors of your platform. This is the platform where you can all mill around, and the nodes of the parallel computer are the train carriages. Okay, so hopefully that's here's a picture. So my train analogy is that we've got a train has drawn up, and these are your nodes. Each of them can have multiple exit doors. This is how many processes from each node are writing. So this is saying we've got 4 nodes, okay, and from each node we're getting rid of data through 2 exits. That means 2 processes are writing per node. We then all mill around on the network, the shared platform, and we're trying to get out through these doors, okay? And that's our way out. But we're leaving. So these are our disks, these four exit doors. This is our network. This is our parallel computer, and these are our I/O processes. So where could you get different bottlenecks? Well, the first thing is if there's a serial exit door, okay, if you're writing to only one disk, then clearly that's going to be the exit. You're going to be able to get people are going to leave the train, okay, at a much faster rate than they can possibly exit. So if you don't stripe a file, there's absolutely no way you can support the I/O bandwidth from all these train carriages from all your nodes. That the bottleneck will be here, okay? So the bottleneck here is on the OSTs. The bottleneck is just getting out of the train platform. The second one is you might do serial I/O, you might do controller I/O, and that's like say you only have a single process writing. Okay, so you're saying, well, everyone has to leave the train by this one exit door. This is controller I/O. We only have a single controller process writing. We've got lots of exit doors from the platform. That doesn't matter. Okay, basically the bottleneck is here. It doesn't matter you have multiple exit doors here, okay, because you simply can't use them. You've got people leaving the train at such a slow speed through this one little door here, or running through through the train. It doesn't matter how many. The bottleneck is here, not here. And so when you do controller I/O, signal process writing, it doesn't matter what you do on the file system level. The bottleneck is here. The other problem you could have is that you might get contention on the network. This just might be too many people, too many files, too many people milling around on the network. We might say, well, actually, the bottleneck might be here. Let's reduce the number of train doors. Let's only have one exit per train door. And here this looks like quite nicely balanced. Again, this is what actually parallel I/O does. Basically, each node is writing with one process, and that is matched up to a door. So this looks quite nice, okay? You've got multiple exit doors, but not too many. Exit doors from the train, multiple exit doors from the platform, but not too many, and not too many people milling around. So you need to match all the way through. You need to match up how many files you're writing, how many processes are writing, how many exit doors do you have. And this is the kind of thing that hopefully a good parallel I/O library will do, will match them. But I find this is quite a useful analogy as to what's going on. So an obvious question when you get a new system is, does the MDS become overloaded for large numbers of files? What's the maximum performance for a single OST? If I was to write to a single OST, what would its performance be? Can one process saturate an OST? Okay. Can a node saturate an OST? Or is the network the limiting factor? How well do different I/O libraries work? What are the best stripe count and size settings? So I wrote a very simple benchmark many years ago to help investigate this, and it's called Bench I/O, and it's what we're going to use. It writes a large distributed 3D array of double precision numbers. So it's exactly analogous to my initial, my default case, a 4x4 array on a 2x2 grid of processes, but it's not a 4x4, it's a much bigger array, it's a 3D grid of processes, but conceptually it's exactly the same thing. This actually came from many years ago. Somebody came to us with exactly that situation. They had a 3D array of they were doing a cellular automaton split across a 3D grid of processes, and they were getting very poor I/O. So they were doing this. Okay. Oh no, they were doing. Sorry, I've got the wrong one. They were doing this. Okay. Had lots and lots of processes writing, but they had they had controller I/O. Apologies. And I converted that to use MPI I/O, and it improved their performance. And then I just stripped all that out and had it as a benchmark. So just a few words of warning. You share HPC resources with all users on the machine. Now you get allocated a compute node exclusively. So your computation speed isn't affected directly by any other users. However, you share the network with other users, and you share the I/O resources with all users on the same files. All the users on the same 12 OSTs will share that. And so when you run your I/O benchmark, somebody else could be doing a lot of I/O and maxing out the disks. Somebody else could be doing a lot of little transactions and maxing out the metadata server. So any can suffer from content. I/O can sometimes be very slow due to congestion. You've probably seen that for an ARCHER2 user. Sometimes it just locks up. That will be somebody doing an unfriendly I/O pattern, unfortunately. So summary, as loss of file serves multiple OSTs. I think of these being multiple disks. By default on ARCHER2, each file is stored on a single OST. That's a strike count of 1. That does give you better performance for multiple files. So that can be a single user writing many files, although hopefully not too many, or multiple users each writing to a single file. But improving performance for a single file requires striping, and that's fully under the control of the user. And we expect parallel I/O libraries to take advantage of striping. We'll discuss a bit later on how that works. So those are my sample results. I'm not going to give you them there. So we're now going to go on to the exercise. So I will share. So are there any questions on that? Apologies, I shouldn't jump ahead. So hopefully you should have a reasonable conceptual model of what a parallel file system looks like. It's not magic. It's just lots of disks, well, 12 here. And we get improved performance, parallel performance either by writing different files to different OSTs, and that distribution is done on the fly at runtime, or if we want a single file, which I believe any rational user does, then you have to stripe that file across multiple OSTs and hope that your I/O library can write to that file in parallel, not do something like have a single process do the I/O. So we will now the machine specs are used. That's a very good question. So are the machine specs are useful because you can see if you're getting sensible results, but basically I think you need a benchmark. It's like, looking at the specs of any parallel computer. You could look at the top 500 list and see what your maximum HPL linpack. It's effectively meaningless. And the problem is if you get anything wrong, you get terrible performance. And that's why parallel. So I have compared to the hardware specs to check that I'm getting something sensible. But I think, that's, you only get, I think you need a benchmark. Your own program can be your benchmark, yeah. So you can, your own can be your benchmark. But I think you need to run real programs under real situations to time it. I haven't found the hardware specs to be a good indication of what you get in practice. Does that help? I mean, yeah, that's my personal opinion. So what we'll do here is I would recommend that you so hopefully. So I would recommend that you get the parallel I/O exercise sheet. So that's opened in a separate window for me, so I'm gonna have to share that window. I actually to test the way that GitHub renders PDFs in line. You can't cut and paste from it. But if you there's quite a delay today, but unless there we are. Yeah. But you can read this here, but the idea is, hopefully, I have tried this morning, but hopefully, yeah, you can follow this setup. So this should work for users in TA. If you're logging in with your own account, you can run these exercises, but you have to run in the standard short queue. If you use your TA216 account for today, 10 till 4 today, we have a dedicated queue of 16 nodes to give you very quick turnaround. But please follow the instructions. In particular, go through these bit by bit, okay? And it is important to do that, okay? By default, there are 3 output directories in the code. You need to configure them correctly, okay? But just go through this bit by bit and see what we get. And I'll stay online. In fact, I could maybe just go through this. Give me a second. So what I will do actually is just so let's just go right back to the start. So this will be useful for the recording for the course. So please do this yourself, but I'll just go through this just to check that it actually works. There we are. Okay, I'm logging into ARCHER2. It's actually login. I have a shortcut, ARCHER2.ac.uk. I've already logged in today, so I'm not going to get prompted for a okay. I'm in the /home file system. I have to go to /work/TA216/TA216 /TA216 hent1. Okay, so that I'm in the right place. Actually, if we look, so Sam, what account are you logging in as? That's weird, because I was able to run this morning. When did you check out the repo? I've updated it today. You may need to git pull again. I don't know. Did you just check it out this morning? Yes. Okay. Sorry. You'll need to do git pull. You won't even have the Archer. You won't even have the November job. You won't have the November job then. There should be. Okay. Sorry. Yeah. So you'll need to do it. Yeah. That's fine. Thanks for a heart attack there. So what I need to do is I'm going to cut and paste this off screen. I'm cutting and pasting this from the PDF. I need to clone my bench.io. There we go. I need to do a couple of module uses. HDF5 may not be, it's not particularly brilliantly supported, but I've just cut and pasted the module load command, and then I have to compile. Oh no, CD into bench.io, sorry. And it compiles the bench, and it's in Fortran for purely for historical reasons. Okay, look. Now if we have these directories called full striped, striped, and unstriped. At the moment, if I was to create a file in the full striped, touch full striped, well, the touch, yeah, full stripe slash test.dat. I did an LFS get stripe on that. You see that it has a stripe count of 1. Okay, it's actually on object storage target 7 out of 12. But the important point is it's not striped. Okay, so I have to actually set these directories to be striping. And if you look at the I'm supposed to do that. If I now create another directory, test2.dat, I do LFS get stripe on that, you'll now see that it is a stripe count of 12 and it's striped across 12 OSTs. Okay, so it's done it in a round robin fashion. It started at 5, 5, 6, 7, 8, 9, 10, 11, and back to 0. So there's 12 OSTs. So we need to do the other ones, which is let's be pedantic and set that. And okay, and now I can do sbatch. If we look at it's this ARCHER2 NOV 25 that we want to run, you'll see that it is it's set up to do a reservation. So use these options for the reserved queue during the course. If you want to run these outside of the session, you would need to do that. So I think you maybe did them in the wrong order. You need to load create HDF5 first. If I do I just did this. So I did this and it worked for me. Has anyone else? So I didn't get that problem. I've tested my account's just the same as yours. Sorry, my account should be the setup same as yours. I didn't get a problem. So yes, I think I would log out. It can get confused sometimes, Eva. I would maybe log out and back in again just to clear the modules. But if you do it in that order, it should work. The first one is just to get ADIOS2. There may be a central installation of ADIOS2 now, but when I last ran this course, there wasn't. So I'm picking up a colleague's one. But so I would log out and back in again and just do the module users again. So I should now be sbatch arch2.job, ARCHER November 25.job, sorry. And if I do sq -- me, I'm pending, I'm running. If I look at the well, it deletes the files at the end, so I may not see the file. That's completed. And this is the bench IO. So you'll see that hopefully you get this file. Basically, it's just it's running one process on one node and writing a 1 GB file with fwrite, basically. And so again, Ed, what account are you using? Are you using the Ed Hod? You said you.
Yeah. So
you can maybe type it in. Which account are you using? Okay, so then you can't run the reservation. So you will need to, if you look at the instructions, can you see my screen? You would need to comment. You need to delete these two and use this. Yeah. You can't use the reservation because you're not in TA. You're not in TA 126. The reservations are project specific. So you'll need to you'll need to change this. Yeah. Yeah. And so you may have to wait a while to run. So if we look at the output, the edge can do a lot of stuff, but it's basically doing it's basically, if you can read it. So we're gonna. I'll maybe just show the. This is just the only reason I'm having a practical session now is just to check that we get the everyday problems like these issues like log E and typos I've made and such like sorted out before the coffee break. But there is, we'll come back and do this. But if you look at this, it's basically doing so I think you maybe haven't done a git pull. Oakley, when did you check out the repo? Oh, that doesn't make any sense. I don't understand how that can be, because I get it here. Can you maybe share your screen? Are you able to share? So there's a little share content button. I'll stop sharing. Yes, it should be. Have I updated the sheet? Apologies, that's my fault. I am sorry. Sorry. There was a run in November 23. So I looked at this and thought, apologies for that. That is my mistake. I will fix that. That is my mistake. Yes, I see. Apologies. Yes, it's sorry. It's because it's, yeah, I see what I've done. So it's, well, no, the sheet is wrong. So the exercise sheet is wrong. I will fix that right now. That is me not reading it case because it said November. I thought it was okay, but it wasn't good because. So I will fix that. Apologies for that. Yeah. Okay. I've yeah. I'll fix that. So that is my not proofreading enough. Apologies. So if you re-download it, I have fixed that. Apologies for that. Yeah, I've fixed that now. So just to go back to my, so if ever, I mean, the idea is you can just check you can run, then we can come back and actually do this after the. But what you will see is that the so basically you only get about 400 megabytes per second. If you do f open, f write, f close of a gigabyte file from a single process, you get half a gigabyte per second. That is not a lot. I mean, remember, an ARCHER2 node has 256 gigabytes. That's saying it's going to take 10 minutes. Yes, it's going to take 10 minutes to write the data from one node, and you've got that. It's just not going to work. So we need to improve that. That is lower than I'd expect, but there have been a lot of system changes recently to help with resilience and such like. So, but you're only getting half a gigabyte per second IO bandwidth, which is not particularly brilliant. But anyway, so I think if I go back to the if I stop sharing and then just go back to the actual again, there's a big right. So the schedule is that we now right, okay. So practical basic IO performance was just to check you can run. I'm going to take a break now, but then the idea is that between 11:30 and 12, you follow through the basic sections, which is set on the sheet is section 5. So what we want to talk is, I'll put that up.